Hi, I'm Rob Persons. I'm a senior field sales architect with Artisan Embedded Technologies. I'm here today to talk a little bit, and I had a great bit here at the beginning saying, well, I've come to VITA again, a sponsored event, to talk about a totally different architecture, but we now have Picming as part of this sponsorship too, so Jerry stole my thunder and my joke on that part. I was here to talk about a real-world solution that we are now involved with a customer who is actually using advanced TCA for another military application. This is not a Navy-based one. We've been talking about Navy for the last few years. This is actually a ground-based application in targeting the Marines. But some of the decision process for actually picking advanced TCA was truly a SWaP-C type of solution. Traditionally, you think SWaP-C, when you hear it in this room, it's going to be some device flying in a UAV, or it's a small device for a man pack, where it really is pretty critical. But there are actually some SWaP-C considerations, even on big systems like advanced TCA, and I'm going to kind of cover some of those aspects here. The system that CSCI, who's one of our partner companies that's actually working and deploying our equipment, is something called a Dynamically Adaptive Secure Computing Area Network, DASCAN. It's really a data center in a box. Some of the things that they're doing with this guy are to take sensor data that's in a forward deployed area, tag it with metadata, and actually then have analysts come through and analyze that data and actually make decisions. So the box is essentially a central switch, some server blades, and an NAS storage for servers. And all this is actually has to be within a two-man lift capable. Again, it's a deployed system. It's out at the tip of the sword, as they say, and has to be able to easily be put in place and actually set up and used. And also virtualized. Sorry, one more tag there. So this, again, is an adaptive system. So they wanted to be able to have the system virtualized inside the box to be able to quickly and dynamically change it as the mission changes itself. So the obvious choices that you could look at are a stack of servers, which is kind of a traditional method for doing some deployments like this. So I've seen these kind of applications used in these systems used in a variety of applications. So you put a top of rack switch in there, you put some number of 1U servers, and you have an integrated RAID NAS device. The problem with that, there are some disadvantages to trying to use an approach like this. What we've seen is really a push in the server technologies to be less small, compact type systems. They're 1U in size and height, 19 inches width, but the depths of them are changing pretty dramatically. Enterprise class servers these days are actually trying to add capabilities by actually adding depth inside the system. And this is fine if you're in a data center where you have a lot of power and you have a lot of space to be able to do this sort of thing. But it's much more problematic when you're trying to work on an application that is going to be deployed and lifted around. There are solutions that you can get. I mean, there are people that are making standard motherboards, and you can do a white box. But the options that you're getting for servers these days is a little bit more problematic and difficult for military applications. The other difficulty with a stack of servers, and they actually did some analysis, and I've done some analysis, and I'll show you. It's very inefficient use of power. One of the things that you're dealing with when you have individual components like this, especially if they're AC devices, you're always having to convert to DC. So there's a stacking effect of inefficiencies between each of these devices. So if you think about it, have top of rack server, you have a NAS device, and those 4 server blades. There's a huge amount of inefficiencies in those conversions. Along with that, there's also infrastructure for those individual servers that take power. Things like fans, things that you may not be using, that add to the total usage, power usage for these devices. And power is a big issue, and you'll see that upcoming in a second here on when you're forwardly deployed. The cost of operating high, inefficient systems is very dramatic. And also, this is a difficult kind of system to maintain. Effectively, they could potentially put these devices on slide rails. Again, we're moving this into a transit case. But it really doesn't lend itself to very easy field serviceability. elements to this. The goal here is they really want to have a system they can maintain in the field as effectively as possible. Again, these are tough systems to maintain in the field, but that was the goal. And having a stack of servers in a transit box is very difficult to try to really maintain effectively in the field. So what they did is they actually started to look at some solutions that they've used in other applications in the past, but it fit very nicely for this new one that they have for the Marines. The system they use is really an advanced TCA system that's a 6-slot. Again, kind of matches that requirement that they would see with a stack of servers. The nice thing about this is that its advanced TCA really does maintain a 20-inch depth. There's no real inherent requirement in the standard itself to say that the systems are going to be of a certain depth, but because of the front blade rear transition module sizes, it really does kind of force advanced TCA to always stay within a certain depth. And that's been something that the Navy's used and in this application as well. So it fits very nicely into a standard transit box. The fact that it has an integrated switch and interconnects really eliminates a lot of complexity for this system from when they're integrating it and actually maintaining it in the field. So everything is inside the system, either the switching architectures, actually a blade inside these systems, and then they have the interconnects are actually part of it. So a lot of external cabling is eliminated and makes it much easier for them to service in the long run. The storage blade was actually an integrated RAID 5 NAS that they purchased from an ecosystem member of Advanced TCA. So it's not our blade. It's something that they were able to purchase within the community. And what made the nice thing about this particular NAS device is that since it's in a blade format, it gives them the ability to actually remove the NAS from the system for security reasons, or if they want to remove it and replace it with another one so they can take this blade out and actually do post-analysis on it. So it's a very nice, easy way to be able to have interchangeable storage options for it. Again, we're going to go back to this efficiency in the inherent design, but if you look at the server blades for an advanced TCA system, they're really designed to be a processor base with really not a whole lot of additional I/O on it. We're not trying to serve all the purposes of a enterprise kind of class operation. So it's a very specific for this type of application where it's just there processing, no additional fans. Cooling inside this box is all centralized in redundant cooling infrastructure, which makes it that these individual components, whether it be a server blade or the NAS blade or the switch, are very, very efficient in how they use power. And then finally, the servicing of the system is greatly improved. This includes just the ability to hot swap blades or to be able to quickly replace broken components inside this thing. But along with that, they can actually have a remote access into it to be able to do some interesting things like disable certain blades. If they have problems with the total amount of power that's available to them because they have a generator that's not operating at full speed, they can actually decommission elements of this system and still have some functionality. Again, going back to that ability to reconfigure it very quickly and to kind of deal with situations that you might see in the field. So that's great. This is all talking about advantages, disadvantages of our system that's going inside this thing, but where does the SWaP-C comparison piece of it come into it? So we'll talk a little bit about that. This is a real world situation. A few years ago, I wanted to go and I did a little bit of a research project in my mind where I tried to compare a comparable stack of thin servers to one of our advanced TCA systems. This is, again, a few years ago, and it was looking at a 10G kind of system, so 10 gig switching, 10 gig blades, but I think it holds up pretty well today in the same sort of comparison. First thing I looked at in this process was to use a stack of servers. I didn't literally get it, but I actually analyzed trying to match exactly the same Xeon's core SKUs, the same memory, the same networking, all that stuff. I really tried to make a head-to-head comparison between these two. So you first start to look at the elements of SWaP, we look at size. Now, technically the stack of servers, since they're only 1U devices, really are smaller than an advanced TCA system. The extra U that we use inside our system is really there to be able to support kind of an enhanced cooling infrastructure. The blades that would go inside this particular box here that you see on the right are really designed to be able to support 350 watts per slot. And so to do that, we need a little bit extra space to be able to go and actually have a dual set of fans that are front to rear cooling, but to also be able to cool more power per slot. But effectively, they both fit within the same size transit case. There's not really that much of a difference in the types of transit cases you can use between a 7U and a 6U system. So, you know, technically the stack of servers kind of win on size, but not on really doesn't have much of an effective, doesn't make much of a difference. Where we start to really see a significant impact is weight. A stack of servers, again, because you have pieces that are not necessarily going to the mission, that you have to replace, whether it be sheet metal, whether it be fans, whether it be additional power supplies, all that stuff adds up. So we see a 40% difference in weight between an advanced TCA, a comparable advanced TCA system, and a stack of servers. And you think, okay, that's fine. Where does that impact the mission? Well, obviously it impacts in several ways. One is it still fits within the two-man lift level, which is what they were targeting. 85 watts is 85 kilos is really kind of getting outside that range of an effective two-man lift. It also has an impact on transporting this out to a deployed area. So this is a forward deployed system. So you have to think about what does it take to get those heavier systems out into the front lines, whether it be by truck, but especially by helicopter. So that also kind of leads into the power aspect of it as well. We saw a 30% difference in power when you do a head-to-head comparison between these two types of systems. And power starts to really show several things. One is the kind of generation systems that you have to have in place to be able to actually operate this thing, along with every other piece of equipment that's in a forward TOC. But it also affects the cost. If you look at the cost of power in a forward deployed type of situation, it can be as much as 15 cents per kilowatt hour. And that, again, if we're thinking about a hostile environment where you're having to fly gasoline or diesel, primarily diesel, with a helicopter, it's significantly expensive in the process of trying to operate this thing. Cost also comes into it when you're trying to move it to the front too. So the weight and cost comparisons really kind of add up together for this entire thing. So we win. But realistically, what we saw with this particular application and what CSCI sees with this application is that any place that you're looking for maybe a stack of servers to solve a problem within the field would be a good application for advanced TCA. One other advantage to these systems is the environments that this can operate in than a typical enterprise class server. There are classes of servers out there that can operate to 50 degrees C, but realistically, that's another inherent piece to this open standard, and it's been a big benefit for these deployed systems.